Hi everyone, thanks for coming. I'm going to talk about a model I've created to predict female mating strategies in situations of sexual coercion. Sexual coercion of females by males is incredibly common across the whole animal kingdom, so I think it's really important to think about the implications of this as a feature of the evolutionary landscape. I've taken a game theoretical approach that considers the expected outcomes when females do and don't resist mating attempts, and that generates predictions of what the most adaptive female behaviour would be given different ecological parameters. I'm also introducing the concept of compensatory resistance, which I'll explain the meaning of shortly. So firstly, what is sexual coercion and why is it so common? Sexual coercion describes attempts by one individual to force, intimidate, or harass another individual into mating with them. We see this in many different forms as a result of sexual conflict over mating. And this arises because, as a general rule of thumb, often females benefit most from a mating rate that's higher than monogamy, but lower than the mating rate that would be the optimum for males. And with this diagram, we can say that until a female reaches her optimum, she's in agreement with the average male that she comes across because it's beneficial to both of them if they mate. However, once this optimum is passed, we reach a zone of conflict where males still benefit from mating, but it's no longer beneficial to this female. And so males will sometimes be selected to increase their own mating rate via coercion, and females will be selected in response to be able to resist that pressure. And this illustrates why I think it's so important to think about sexual coercion, because female strategies for how often they mate are often going to be deployed in an environment that already has this directional pull. So they can't just straightforwardly decide how many times they're going to mate. There are several reasons that females are expected to sometimes resist mating attempts. Firstly, as a general principle, mating is costly. That's not just a cost of reproduction, but a cost of copulation just in itself. There's strong evidence from several model species that mating reduces lifespan in both males and females. This can be for a number of reasons, including penile spines, which wound females, and that's some penile spines of a garter snake on the bottom right there. Also, compounds in ejaculates can be damaging to female fitness. And in the top right is a figure from a classic paper by Chapman et al. Showing a really strong effect on survival of female Drosophila exposed to these proteins via mating. And then at a more basic level, there's factors like time and effort or potentially increased predation risk. So any female that can use resistance to avoid matings at a surplus to requirements is going to reduce these costs, so that's a benefit. Resistance can also be beneficial by using it selectively as a form of mate choice, or because of a sexy sons effect, which happens because offspring are more likely to be sired by males who are better at overcoming resistance, leading to sons with those same traits, and therefore higher inclusive fitness for the female. And it's the first benefit that my model explicitly focuses on, but it could, in theory, look into these other effects as well. And that brings us to the main question I want to ask, which is when to use resistance. We've seen that resistance has benefits, but it also has costs. Resisting might prolong or intensify sexual harassment, or it might mean missing out on a resource or spending time in a less desirable area if you're avoiding males. There's also the chance it could be over-effective and prevent matings that would actually be beneficial. And one important thing to factor in when answering this question is how successful is resistance likely to be? There's lots of variation in nature as to how much control females have over copulation. In many insect species, it's almost impossible without cooperation from both sides. Often the female is larger than the male, and she might have to cooperate by allowing the male to approach or by holding her abdomen in a certain position. Or if males attract mates by chirping or releasing pheromones, she can simply not approach. And on the other hand, there are examples of resistance that's much less effective. In a paper about the behaviour of orangutans, it's reported that, quote, the majority of copulations observed in this study were forced and involved protracted struggles between females and males. And the author, John Mitani, says that females manage to struggle free less than 10% of the time. So from this, we can conclude that if the female's behaviour is adaptive, either it must be very cheap to engage in resistance, or forced copulations must be very costly, so that it's worth resisting even with this small chance of success. And it's because resistance isn't 100% effective that we expect to see this phenomenon I'm calling compensatory resistance. Just as in the previous diagram, we see different optimum mating rates for both sexes here and a zone of conflict once the female's optimum is passed. If a female strategy was to resist mating once it's no longer beneficial, we might still see some forced copulations depending on how effective her resistance was, and so she would potentially overshoot this threshold. Compensatory resistance would be if females switched on resistance before reaching this target to compensate for the expected effects of sexual coercion. So it's like stepping on the brake before the point where you actually want to stop. And often this is going to be the optimal strategy, which means you could see only a small amount of receptivity, but have that reflect an optimum mating rate that's higher than that might suggest. So we've seen that often females won't be able to directly choose how many times they mate. What they can choose is how many matings they accept or solicit, and that will map to some number of matings that actually occurs, which might be higher. In this model, we say that females expect to receive a certain number of mating attempts, and of those, they can choose how many to accept, and the remainder of attempts are resisted. And if we know or estimate how effective resistance is, expressed as a probability that copulation is prevented, then from that we can say how many matings we expect to actually occur, which will be the number accepted plus the number that are unsuccessfully resisted. We then model a function that gives us a fitness payoff of any given number of matings, which you can see plotted on the right. This function has an exponential term representing the benefit of mating, and that saturates with increased matings. And there's also a constant cost per mating, which is subtracted to get the net benefit. And you can get different shapes of payoff curve by manipulating the parameters, but it always has this peak marked by a dotted line here, which is the maximum possible fitness payoff. So to get the expected payoff of a certain number of acceptances, you take the number of actual matings that it's expected to result in, number 2 on the slide, and you read off this payoff function what payoff is expected from that number. We also want to account for the cost of resistance, so we'll have a parameter for how costly resistance is, multiply that by the number of times we resist, and again subtract that to get the net benefit. And like the graph on the right here, that payoff for that function for the payoff of any given number of acceptances is also going to have a peak. And we can differentiate the function to find an equation for that peak. In other words, the number of acceptances that gives the highest payoff. Unfortunately, there's not time to get into the maths of all this here, but if anyone is interested, please feel free to ask about it. So we can use this equation given by step 4 to look at how varying any of the parameters affects the optimum strategy. And as an example, I've plotted the optimum number to accept against the cost of resistance. And as you have higher and higher costs, females benefit by resisting less and less. Crucially, even though the optimum number of times for them to mate has not changed. And one of the cool things about this model is that it predicts 4 distinct cases of behaviour. And these are very neatly predicted by distinct ranges of a parameter defined by a combination of the values discussed on the previous slide. Though again, there's not time to get into the detail of that. But you can see from the graph that beyond a certain threshold cost of resistance, there's no solution. And that's the area we call case 1. And very neatly, the threshold resistance value is always equal to the cost that you expect to save by resisting. So if the cost is greater than the expected saving, it's never going to be optimal to switch to resistance. And that's known as convenience polyandry, where you always accept not because copulation is desirable, but because it's not worthwhile to resist. Case 2 up at the top is where the optimum value predicted by the model is above the number of attempts a female expects to receive. So she can't possibly select that number to accept, and the best she can do is just always accept. And we expect to see this perhaps in solitary living species, where a limiting factor on female fitness might be the number of males they encounter. So we see the same behaviour, always accept, for both case 1 and case 2, but this illustrates that there's 2 very different underlying reasons. Case 4 is kind of the mirror image, where the optimum given by the model is below 0. So since you can't accept a negative number, the best strategy is to accept 0 or always resist. We expect this case, as well as case 1, convenience polyandry, to be found in nature in situations of intense sexual harassment. And case 3 is the Goldilocks zone in between cases 2 and 4, where the best strategy is to accept a certain number and resist the rest. What can we conclude overall from this? Firstly, there's the idea that females might do best by resisting some copulations that actually would be beneficial to them, to make up for the effects of sexual coercion, and we call that compensatory resistance. And relatedly, from this model, there are really significant implications for the interpretation of female mating behaviour. For instance, if females are more receptive to one male phenotype than another, you might assume that that's because it's more beneficial to mate with that phenotype. However, this model implies that we have to consider whether the discrepancy could be partly or wholly explained by proximate factors, like it being harder or more costly to resist different phenotypes. That's the end. Thank you very much.